Welcome to this episode of At Home with APS. Hi, my name is Tammy Gaudette, and I will be with you for 4th and 5th grade math. So let's start it off. We're going to start with a problem called an open middle problem. And this problem is a little different than what you might be used to. What we have to do is we are only allowed to use the digits 1 through 9. And we cannot repeat them. So if I was to look at this, I have 2, 4, 6, 7 spots that I could fill. And I am looking at equivalent fractions. So we got to remember what equivalent fractions are. In the aspect that we have a fraction that has to equal each other when reduced or has the same equivalent of a whole or pieces of a whole. So if we look at this, and I'm going to try, let me try 1/2. And if I multiplied 1/2, the top and the bottom, the numerator and the denominator, by 2, I would know that my new fraction would be 2 over 4. So I have now used the digit 2 again. So does this work? Nope. That's a bummer. That won't help me out at all. Let's try 2/3. So if I do 2/3, I'm going to try an equivalent fraction. So I multiply the numerator and the denominator by 2. I have here 4/6. Awesome. It's working so far. I do not have a repeat of any of my digits. So I'm going to multiply 2/3 by 3 now. I'm going to put a little just 3. Probably can't see that. But if we do 2 times 3 is 6. 3 times 3 is 9. I have a copy of my digits. So that does not work. So I'm going to give you a second, and I want you guys to think about what could you start off with that would help you out to be able to get a digit where none of them repeat. So I'm going to give you a second. All right. Have any idea what you have? Have something? All right, I'm going to go back to my first one. My 1/2 and my 2/4 didn't work. But if I kept working through that, I have 3, 6, 4, 8. So I keep multiplying 1/2 by 2, by 3, by 4. And then if I keep going, 5/10, 6/12, 7/14, 8/16. So I see here my 2 and 4 work. My, which other ones? 8/16, 9/18. My 9/18 work. And do I have another one where it work? That won't work. My 4/8 won't work. My 3, there we go. So I have here, if I put in here 2/4, 3/6, and 9/18, that works with that. Now this is only one of the problems. There is many more out there that you could do. So think about another way that you could solve this using different equivalent fractions. So our next thing that we're going to be doing is I introduced a term to you guys. Equivalent fractions. So you may have seen this before, but this is what's called a Frayer model. What you would do is you would take a sheet of paper, you'd fold it like a hot dog, fold it like a hamburger, then you would find the edge that has no open. See, here we have a lot of open areas. You find the edge that has no open areas and you fold it down in a little triangle. That ends up, when you unfold it, gives you a diamond in the center. And it gives you 4 quadrants. So that's a quick way you can make an easy to do yourself Frayer model template. So we have here equivalent fractions. With this Frayer model, what I'd like you guys to do is we're going to have 4 sections that we're going to fill out. We're going to fill out the definition. We're going to fill out a representation. We're going to do an example. And again, our examples, because we're in math, we always want them to be a math example. And then over in this last, we're going to want a non-math example. So with this, the definition of an equivalent fraction. Thinking about equivalent and what we did here, we want it to where it is a fraction that has different numbers for the numerator and the denominators, but is equivalent, is the same amount. So if we were to write that, it's a fraction with different, and I'm going to abbreviate that, so DIFF is different, numerator, and I'm going to check my spelling because I sometimes need a little help with that. Denominator, that represent the same value of the whole. All right, guys, I hope you're really into math because this is like, I get all excited, be able to get here and do something different instead of sitting there playing video game like my son. He's sitting there and I have to encourage him to do many different things. So I'm excited that you're here with me today. So with my representation, I'm going to do a pictorial representation. For example, 1/2. Two-fourths, if I was to draw that, I would take my half, split each half in half to get my fourths, and then I'd color in 2 of them. And I'll do one more. So let's do 3/6. So I take my half, split it into thirds, and since it's 3/6, I'm going to color in 3 of them. So we can see with equivalent fractions, even though the numbers are different, they still represent the same amount, the same value. So 3 out of 6 is the same as 1 out of 2. Then if we were to do an example down here for our math example, I'm going to use 2/3. If I take 2/3, multiply both the numerator, which is the top, and the denominator, which is the bottom of the fraction, by 2, I would get 4/6. So I know that 2/3 is the same as 4/6. And I'm going to do another quick representation to make sure that has some proof there. With math, you always want to have your reasoning, your proof of why that is true. So what I'm going to do is I'm splitting each of my holes into thirds. The top one, I'm going to color in 2 of them. 1, 2. And the bottom, I has 6ths, not thirds. So I'm going to split those in half, the thirds, to get my 6th. 1, 2, 3, 4, 5, 6. And then I would color in 4 of them. 1, 2, 3, 4. So again, my 2/3 is equivalent to my 4/6. Now I'm going to go into a non-example. Again, math. So I'm going to use, since we're talking about equivalent fractions, I'm going to use 2 fractions I know that are not. And these are our benchmark fractions. So if we think about 1/2, and since I've been using thirds, I'm going to use 1/3 also. Do you have any idea which one's bigger? Let's find out. So I'm going to again do a representation because that's a quick, easy way to prove it. So I have my half, I have my thirds. I'm going to color in one of my halves and then one of my thirds. Was your guess correct? Awesome. So we have now done the Frayer model of equivalent fractions. We've given a definition, we've given a representation, we've given a math example, and we have also done a math non-example. So be thinking about that. Every time I see you in the next couple of weeks, we're going to be looking at some different ways to see our vocabulary and be thinking about that. So we're going to move into a book that I have really, really liked and I've used several times with my classes. And in this book, they talk about on the day you were born. So my question to you is, do you remember the day you were born? Well, I don't. I'm thinking I don't want to say how many years ago that was, but that was a few years ago for me. I remember the day my son was born, but of course I was a little older when I had him. So do you have a memory that you remember was the earliest memory? Think about that for a second. What was your earliest memory? My earliest memory, you're going to laugh, is I remember that my dad was in the military, so we moved a lot. And I remember one day when we were moving, if this is inappropriate, I'm sorry. But I know kids, you'll love this. What happened was I had to go to the bathroom, and I must have been 3. So my mom said, go in your diaper. And I was like, no, I don't want to go in my diaper. So I learned how to potty train myself, and I went to the bathroom in the bathroom. So yes, that's a little joke that my mom and dad laugh about a lot when they tell people. So that is my earliest memory. Now what I'd like you guys to do is think about if you have something called a birthday twin. Do you know what that is? A birthday twin is someone who was born on the same day and same month as you. It's not like a normal twin where you were born on the same day, same month, and same year. This is just on the same day and same month. So I was born on July 14th. And it just so happened that I do have a birthday twin. My birthday twin is my Aunt Janet. And she, of course, was born years before me, but was born on the same day, July 14th. So I have always thought that was the coolest thing that my aunt and I share to date. So think about, what is your birthday? I have went ahead and I've got some birthdays up here that I have asked several people around here of what is their birthday. So if you're looking at this, we have December 5th, December 20th, February 20th. We have many birthdays up here, just random dates. How do you think we could organize these? All right, I'm going to organize them in what we call a line plot. And what a line plot is it is going through and you have the months here, and then you have from there, we put all the dates. So we're going to organize them in an organized fashion. So what do you think would be the first one that I would take? January. Yes. So there we go, look, and we have to see if there's any January's birth dates. I don't have any. So we'll start with February. I see a February, a March. So I'm going to start my line. So I'm going to start with February, March. I see some Aprils, another March. So I'm going to continue putting these all up there. And while I'm doing that, think about your family birthdays, and if you have anybody that you know who has a birthday close to you, or if they're like on the opposite ends and maybe they're a half year different from you. So, while I'm doing this, have you thought of any birthdays that you have that you're close by, or your relatives' birthdays, siblings? Whoa, I'm noticing a pattern already. Have you noticed that pattern? Whoa. I don't think I'm that tall. Holy moly. And then R12s. So, if we were to look at this, what patterns did you see? People over here are saying, whoa. So I noticed there's nothing in January. Right now, January is the only month that we have no birthdays from people around here. I noticed that March has a few. And yes, we noticed August. Did we have any birthday twins in our data? I noticed that we actually had birthday triplets. So what do you think that is? That is, we have 1, 2, 3 people who were born on August 27th. Kind of cool, huh? So then we have triplets. Did we have any quadruplets? That means 4 people? No? Okay. So in this, if we were to talk about some in data statistics, we always talk about several things. One of the things that we talk about is the mode. So I bet some of you have already had this term and some of you may not. So with the mode is something, a number that is repeated the most often. If we were to talk about our month, which month was repeated most often? August. If we were to talk about the date, like the 27th, that would be our mode, but we're talking about the months. So right now, August is repeated the most often, so that we would have our mode. In that, I'm going to be looking at a book, reading you a book, and in that book, I would like you guys to be thinking about, so let me go get ready for this actually. Whoa! So, I'm going to be reading a book, and what I'd like you guys to do is, in this book, I'd like you guys to think about what was the author wanting to portray to you, what math might be involved in this book, since, of course, we're talking about math. And just be thinking about what's your favorite part on this book. So this is a book called On the Day You Were Born by Deborah Frayer. And the publisher is Hardcore Incorporated. So here we go. Again, be thinking about what is the author wanting to write this book, what math may be involved, and also your favorite part. So on the day you were born, for Mother Earth, born 4.5 billion years ago, and baby Kalia, born June 1st, 1988, and you. I think baby Kalia was her daughter. On the eve of your birth, word of your coming passed from animal to animal. The reindeer told the Arctic terns, who told the humpback whales, who told the Pacific salmon, who told the monarch butterflies, who told the green turtles, who told the European eels, who told the busy garden warblers. And the marvelous news migrated worldwide. While you waited in darkness, tiny knees curled to chin, the earth and her creatures with the sun and the moon all moved in their places, each ready to greet you the very first moment of the very first day you arrived. On the day you were born, the round planet Earth turned towards your morning sky, whirling past darkness, spinning the night into light. On the day you were born, gravity's strong pull held you to the earth with a promise that you would never float away. While deep in space, the burning sun sent up towering flames, lighting your sky from dawn until dusk. On the day you were born, the quiet moon glowed and offered to bring a full, bright face each month to your windowsill. While high above the North Pole, Polaris, the glittering North Star, stood still, shining silver light into your night sky. On the day you were born, the moon pulled on the ocean below, and wave by wave, a rising tide washed the beaches clean for your footprints. While far out at sea, clouds swelled with water drops, sailed to shore on a wind, and rained you a welcome across the earth's green lands. On the day you were born, a forest of tall trees collected the sun's light in their leaves, where, in silent mystery, they made oxygen for you to breathe. While close to your skin and as high as the sky, air rushed in and blew about, invisibility protecting you and all living things on earth. On the day you were born, the earth turned, the moon pulled, the sun flared, and then, with a push, you slipped out of the quiet, dark quiet, where suddenly you could hear a circle of people singing with voices familiar and clear. Welcome to the spinning world, the people sang, as they washed your new tiny hands. Welcome to the green earth, the people sang, as they wrapped your wet, slippery body. And as they held you close, they whispered into your open, curving ear, "We are so glad you've come." And then what I love about this book is next they talk about migrating animals, pulling gravity. They talk about the little bit of science that's behind in this book. Now, I had asked you to look for 3 things while you were reading. Why do you think the author wrote this book? Why is she telling us this story? I'd also asked you to figure out, what do you think the math would be in this book? And then I had asked for you to think of your favorite part. So the author wrote this book because she's really big into all the science part of it, but also for her daughter, because that is a big day when you have kids and those kids are born. As my son is, he's now in 7th grade. Lucky him, and he's in the middle of middle school, which is the best of years. And he also was one of the best thing. He is my little angel that I was able to have, and on the day he was born. So I know that's one reason that she wrote this. The other, I had asked for what was the math behind this. In just a second, we're going to go over and do a math activity with this that I'm going to ask you to do. And then lastly, I had asked you what was your favorite part. My favorite part, when we look at this, we talk about at the very bottom, the very end of it, this part right here, where they're singing to each other. This reminds me of when my son was born and how happy my family, my extended family was when he was born. And there's one of these books that I have that it talks about growing old, and I cry every time. So I really, really love that piece of this. So I had asked you to think about the math involved in this. So what do you think we're going to be doing with the math involved in this? On the day you were born. So we're going to figure out how many years it's been since you've been born. Most of you, I bet, could figure that out. 9, maybe 10 years, maybe 11. And then some of us, mine's been a little bit longer, so we're not going to go there. But then we're going to figure out how many months. So if we were to figure out how many months it's been since you were born, how could we do that? With that, we know how many months are in a year. 12. So we have 1 year equals 12 months. So how could we use that information to help us complete how long it was, how many months? So we would take 12 times the number of years. So we have, I'm going to say 10. I'm 10 years old. Don't I look it? Yay. Times 12 would give us the months. So what is 10 times 12? 120. Good. So from there, if you were a 10-year-old, you'd be 120 months. But, right, yeah, I bet you caught me on that one, is you may not be exactly 120 months. Maybe you're 10 years and 2 months. Maybe you're 10 years and 4 months. So you got to add on those extra months here. So if I was an extra 4 months, I would add that on, and I would have 124 months. So make sure to do that. Now we have the years, months. Now you guessed it. I'm going to ask how many days old you are. So how are we going to figure that out? Because not every month has 30 days in it. We know that some months have 30 days, some months have 31 days, and then we have this oddball month, February. February doesn't have 30 or 31 days in it. So you have to take that and know that how many days in a month are there. So we have January has 30. I'm getting ahead of myself. So really fast, let's go back to our year and month. If I was to say 1 year, how many days would be in 1 year? 364 days. Did I get you? It's 364 and a fourth. So every 4 years we have a year that's called a leap year, where we add in an extra day into February. So on most years, we have 364 and a fourth, And then we know that much to help us out with the years, the 10 years. But then when we have to figure out the extra months, we got to add in that one. So I was born in July. I would have to have my years, I'm going to use 10 to make it easy on myself. My 10 years. I'm going, since I'm figuring out the days, going to multiply it by 364 and a fourth to figure that out. But I'm born in July. So I have to add in those extra days and months from those extra months, those 7 months. But how can we figure out how many days in a month? Does anybody remember the little trick? And I know there's many out there, and I know of one of them that comes to my mind right away. So if you put out a fist, and you talk about your knuckles, every time you're on a knuckle, it's 31 days. Every time you're in between, it's 30 days, except for February. So like January would be 31 days, February would be normally 28 or 29 in a leap year, and then March would be 31, and so on and so forth. And then you move on to the next hand. So July and August both have 31 days in it, to give you that little hint on that. So if I was to do that, I'd multiply this by 10, and then I'd have to add in my extra months, which is 30, February, 28, March has, January is 31, right? Has 31. Hey, did anybody catch me on that one? Remember, your job always is to catch your teacher's errors, because sometimes they throw them in purposely, and sometimes they throw them in by oops, like I just did. So March has 31, January, February, March, April has 30, May has 31. Is this right? Yes. June. See, now I'm even double guessing myself. You know what? We all do that. And then sometimes we just need to talk ourselves through it. And then in July, I didn't take the full 31 days because I was born on July 14th. So how many days do you think I would add in July? I'd add in 14. So I would have to figure this out. Then I would have to add in all the extra days for this year to figure out how old I am. So what I'd like you guys to do is now figure out for your own how many years old, how many months old are you, and then figure out how many days old. While I do my calculation really fast. So I'm going to take, probably should do it up here instead of on a paper. So I'm going to take 10 times 364, so that's 3,640. And then I have to take a fourth times 10. Times 10. So we're going to do that. I have 10 fourths, which is, well, I have 4 fourths as a whole, 2 fourths. Sorry, what I'm doing is I'm taking 4 fourths and 4 fourths equals 8 fourths. So that's 1 day, 2 days. So I can add it in, that's 2 days. And then what's left over from my whole is 2 fourths, which is a half. So I have to add in an extra 2.5 days. So if I was to do this, I wish I had my little calculator handy, and I don't. Yay, for me. So we have 31 plus 28 plus 31 plus 30 plus 31 plus 30 plus 14, and then my 2.5. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5. That's 15, 16, 17, 18, 19 and a half. So I have 197 and a half. And if I add that to my 3,640, And again, please catch me on any math errors that I may have had. 8. So if I was 10 years old this year, the number of days old would be 3,837 and a half days. So I'd like you to try to figure out your own and use that to have a fun time, because I've done this with my class many years and we have really enjoyed to figure out how many days old each of us are. Next, we're going to be having someone join us. And what we're going to be doing is a game called Multiplication War. Come on up. So, introduce yourself.
Hi, I'm Dr. Webb.
So in Multiplication War, you will need a deck of cards. And in this deck of cards, what you will need to do is take out all your kings, jack, queen, kings, and jokers. So I am going to do that of all your suits, all 4 suits. I'm going to do that. And then what you need to do is shuffle your cards. So my mom, one of the things that she has always told me about is when we lived in Germany. So remember, my dad was military, so I've lived all around. And when we were in Germany, my mom and dad were playing cards with some Germans. And she started to shuffle and do what we call the bridge, where you bring it back together over that. And what all the Germans did and looked at my mom and pointed, card shark, with a German accent. So I thought, I love that. That was one thing about Germany. Oh God, I love Germany. So then what you do is you take what's left of your deck of cards, and you just evenly distribute it to both of your players. So I'm going to do that really fast. And from there, what we're going to do is then you take that and you play very similar to regular war. But what happens is you're not just looking at the biggest number.
Okay, don't just look at the biggest number.
No, don't look at the cards.
What?
Nope, don't look at the cards.
I can't look at the cards?
No, you can't look at the cards.
Okay.
Because if I was looking at the cards, I could just pull out the biggest number every time, right? And then I'd just easily win, and that's not how we're going to do that.
That's not how we play the game? Okay, we have to social distance now. Yes, it's that time.
All right. So what you do is, so we're going to hold up the cards, and then we're going to put them down. And we held up the cards so you could see them. But what you do is we have a 10 and a 4. And the rules state is both of us are going to try to multiply those 2 cards together as fast as we can and say it first. If we say the product first...
40.
I guess she won the cards, just like...
Is that how you play?
Yes, it is.
Okay.
So she would get the 2 cards. Now... You're trying to win, trying to get all the cards, just like a war. You're trying to win all the cards away from your partner. If you say the product at the same time, just put the cards off to the side, and then you'll flip over in the next group of cards, and whoever wins that round wins all of those cards, including the ones from before. So, you ready?
I hope so.
All right. So let's show them first. All right. That's a 1. Oh, I'm sorry. Ace is a 1, so it's 6. Sorry, aces are 1s. I apologize. That's one thing that I did not say. So let's show them again. Okay. 2.
That's right.
50.
You've played this before, right?
No, never. I played a lot of math family nights.
14.
You notice I'm very competitive.
Just a little.
18. Up, we said at the same time, so we put those on there.
In the tie pile.
In the tie pile. So that whoever wins the next round is going to get them.
Okay.
So here we go.
1. Tie pile.
Tie. 20.
That's correct. Oh,
Yeah,
you get the whole pile.
I get all of them.
Oh, okay. 18. Tie pile.
Tie pile. So you notice I'm second guessing myself.
18.
Nope. It's 27.
That's it.
See, this is the one that when we were playing this earlier, Dr. Webb and I said 18.
You did.
So what it is if you said it wrong, if you get it wrong, you automatically don't win that round. So, but the other person has to get it right to still win. Otherwise, it goes back in the tie pile, and you have to move on. But because I said it.
Go right ahead. 45.
All right.
Yay. 64?
Yep.
I'm trying to remember.
I know, right? See, this is why we're playing it. Even us, we're sitting here. You notice we take some time sometimes answering it. 72.
72 is it.
So we're having to remember our facts. And this is a good reason to play this, is it just gives us a fun way, 12, to remember our facts. Now, one thing.
56.
Yeah, she started saying, I just went with her.
Thank you.
I'll be honest. 70.
Yes.
So one thing with this is if you have an older sibling, 18.
Yes.
Yes.
I didn't
Okay.
finish it.
Okay.
14.
So if you have an older sibling that can play with you, 24, what you could do is 50. Oh, that's the same. So what you could do if you have an older sibling and they're calling it out way faster than you and you're having trouble keeping up with them, what you could do is instead of just flipping over one card at a time, you both try to say the answer to the 2 cards, is you flip over 2 cards, your sibling flips over 2 cards, and then whoever gets their answer first, their correct answer, can get all the cards. So it's a way to give you a time to say yours and look at yours, instead of having your sibling just automatically take it from you right away, because I had that sibling.
Okay.
So thank you so much.
That was a great game. I really enjoyed it. I hope you guys enjoy it as well.
So again, you'd keep playing. You notice Dr. Webb had like no cards left, and I had all of the cards. You would keep playing until one person had all the cards. So that was Multiplication War. Please have fun and enjoy that game. I have always used that one with my kiddos when we were in class, and also at math family nights. So our last activity that we will be doing is a problem, a task that I have used several times with different schools, different districts across New Mexico, and I'd like to see how you do with this task. Now, the reason I brought up this task is it is one that has multiple ways you can solve it. It doesn't just stick with one way. All right, hold on. I'm having to stretch. All right. It doesn't have just one way to approach it. You can approach it from multiple ways. And that's why I love these problems. Now with this, I'm going to pull up because I'm one of those ones who likes to write on a lot of paper. I can't just not write around. As you can see with this one, I wrote all over the place, right? This is what math is. It's messy, it's dirty, but it's so cool. And that's what I want you guys to be thinking, is just try it out. It's okay if it's messy, dirty, just as long as you know where your answer is and you're able to explain it to someone else and show where that answer is if you turn it. As you notice, I tried to circle mine right here. No, I didn't. Ooh, bad on me. So I'm going to square my answer since I circled several things. That was my bad. Okay. So with this one, We are in a wheel shop. We have multiple wheels, bikes and trikes. So it says the cycle shop on Main Street sells bikes, 2 wheels, and trikes, 3 wheels. Yesterday, Sarah counted all the cycles in the shop. There were 7 bikes and 4 trikes. How many wheels were on these 11 cycles? Show your calculations. That was the first question. So before I go on to the next one, I'm going to get a hot pink, purplish color. And we're going to circle the important information we need to know about this to be able to solve this task. And then we're going to underline what do we need to solve. So let's start with the underlining. What do we need to solve in this first question? How many wheels? So we're talking about wheels. So I'm going to underline the wheels. We're there on these 11 cycles. So we need to figure out the wheels. What information, I'm going to circle the information, do we need to know that? We have 7 bikes and 4 trikes. And really fast, what is a trike? Tricycle. So we know that a tricycle has 3 wheels and a bike has 2 wheels. So how could we figure this out? One way that I have that we could figure this out is we know a bike has 2 wheels. So, and I have 7 bikes. Wrong marker. So we're going to take 7 and multiply it by the 2 to figure out that we have 14. Then for the trike, the tricycles, I've never heard of them as trikes. So this is going to just, don't let the vocabulary get you messed up. We know we have 4 trikes, and there are 3 wheels each. So I have 4 trikes for 3 wheels. So what is 4 times 3? 12. Then what do you think we're going to do to figure out how many wheels do we have? We add them. So we have 14 plus 12 equals 26. And as I always tell my kiddos, we need to always put the units. What are you solving for? We're solving for wheels. So I put 26 wheels. So I'm going to go ahead and circle my answer. So that's question number 1. Now you could have done it multiple ways, and that's in a little bit I'm going to ask you to try to solve it a different way than I solved it. So the second one, we have today Sarah counted all the wheels of all of the cycles in the shop. She found that there were 30 wheels in all. There were the same number of bikes as there were trikes. How many bikes were there? How many trikes were there? And show how you figured it out. So for this one, we got to circle and underline what we're solving. So let's first find out what do we need to solve for. So we need to solve for how many bikes? What else do we have to solve for? How many trikes? And one thing last time I forgot to mention with this one, the one thing piece that always says show your calculation, what is it asking for on this one? Show how you figured it out. So you can't just say, oh, it's 26 wheels, yay. No, we can't do that. So remember, anytime we're wanting to know how you're thinking. We just don't want to know how you got the answer, because anybody could yell out the answer. But what's most important is how you got there. And I really want to emphasize that, because we want to know how you got there, not just the answer. I gave you the answer. Now, just like later on, I'm going to want you to show me another way to get there. So if we have the many bikes, how many trikes, and now we need to circle what information do we have that will help us. we have the 30 wheels, right? So we have 30 wheels. We know there are a combination of bikes and trikes. What other piece of information do we need to know? And I'll tell you right now, a lot of us skip over that piece of information. Yeah, right? It's even underlined for you. Same number. So I have to have the same number of bikes and the same number of trikes. So the way I like to do this is I'm really big on tables. So I go ahead and I'm going to start with my bikes, my trikes, and I'm going to do a T-chart, but I'm going to add an extra piece on that. We have bikes, we have trikes, and then the number of wheels. One piece of information that I like to put in my table is how many wheels of each one. So a bike has how many wheels? 2. A tricycle or a trike has how many wheels? 3. So I put that information because it helps me remind me that I'm not just counting the bikes and trikes to get to 30. Right? If we did that, how many bikes and trikes would I need to get to 30? 15 each. But that's not what it's asking. It's not asking for the bikes or trikes. It's asking for the number of wheels. So next, what we do is I'm going to do one bike, one trike, and then how many wheels would that be? I know one bike is 2 wheels, and one trike is 3 wheels. So I'm going to do 1 times 2 is 2, 1 times 3 is 3, 2 plus 3 is 5. So does that get me to my 30 wheels? No, let's try another one. So can I try like 1 and 2 or 2 and 1? No, right? Because it has to be the same number. So knowing that, I'm always going to have the same digit for both of them. So let's try 2 and 2. So again, 2 bikes, 2 wheels each is 4, and 2 tricycles and with 3 wheels each is 6. So 4 and 6, add them together is 10. So let's try one more. I'm going to do 3. I'm going to make this where I'm just going to keep going up and up and up. So 10 did not make us our 30. That's why we're continuing on, is we know we have not hit the answer we're trying to look for. So again, you notice I'm double checking back and forth each time. So I have 3 bikes at 2 wheels, 3 trikes at 3 wheels. So 3 times 2 is 6, and 3 times 3 is 9. 6 and 9 make 15. Ooh, I'm almost there. So this is what I would like to leave you with, is I would like you to attempt both number 1 and number 2. Number 1, I've given you the answer. I want you to show me another way that you can do that. Number 2, I want you to keep going, and on Thursday, or the next day we see each other, we're going to check your work and see what you came up with the way I came up with it. So that's what I'm going to leave with you. Thank you so much for joining us on this episode of At Home with APS. Have a great day.